Coming back. So we are resuming. Okay. So we are resuming here. Sorry about that, ladies and gentlemen. Temporarily lost our internet connection. So you're reading this table. That first row tells you how many people survived. Is that right? And if I go to Excel, okay, as you guys can see, now we're in Excel. That first row right in here says 706 people survived. Okay, how many people did not survive? Notice I used the complement. Did not survive. What does that mean? If you didn't survive, you died. How many people died? 1,517 people. Is that true? So if you count right over here, the number of survivors and the number of people who died, what do you think this number means? 2,223. It's total passengers. Good job. You guys okay? That's great. How to read a table. Now, let me ask you this question. How many men were on the Titanic? You say, I don't know. Well, what does it say? 1,692 men were on the Titanic. Is that true? Well, what does this 332 mean? You're in the survive row, man column. Survive row, man column. What do you think that means? That's how many men who what? Survived. How many men died? 1,300 and what? 60. Go to the women now. How many women are on the Titanic? 422. 318 survived. 104 died. How many boys are on the Titanic? 64. 29 survived. 35 died, okay? How many girls are on the Titanic? 27 survived and 18 died, okay? So, ladies and gentlemen, this is how we read the table, rows and columns. So, they didn't even ask you to count here, did they? Right? You guys notice you're not even counting here on that. Okay. Just reading that table now. Here's my questions to you. I got that same table here. We're going to warm up today. So I want you guys to answer these questions. Here's the warm-up. They say, if you select a passenger at random, what's the probability? This is a probability question. It's not odds. What's the probability of selecting, what's the first question? A man. You guys okay with that? It's a probability question. This is your event, selecting a man. What does question number 2 say? Selecting a non-who man. Interesting. What is that? Non-men. Isn't that the complement? What's that? Exactly. Anybody else but a man. What's the next question? What's the probability you're a who? A boy. And then what's the probability for the next question? You're not a boy. Everybody else but a who? Boy. And then look at this question. What's the probability you're a man and a what? Boy. What's the probability of surviving? And then what's the probability of another complement, non-surviving? So this is kind of going over some of the things we talked about yesterday. And then look at this question. What's the probability you're a man or you're a what? Boy. So there's a few things I want to talk about today. The word and, the word or. We got some probability formulas for us, but I want you guys to look at this, answer some questions based on your probability definition. In other words, you say, what definition? P of E. Do you guys remember that? It's in your notes. So this is a combination of seeing what you already know as a review and then introducing something new as well. So we're covering a couple of bases here. Now I'm going to give you guys some time for these questions because These questions are going to require you to think. Is that true? So we're going to have to think about some of this stuff. So ladies and gentlemen, hopefully you have those questions down, copied, right? Because I have to put up the table for you. So let me put up that table here. Maybe you can see it a little bit here. I don't know. Okay, you guys have that copy, those questions? Okay, then we're going to answer based on the table here. All right, good job. All right, let's try to see what happens here, okay? So what's the first question in this? What's the probability of selecting a man? Okay, so question 1, here's how we look at this. I put P of M. What's the definition? Do you guys remember? If I try to get this, let's get this straight here. Question 1, probability of selecting a man. You need to know the number of men divided by the total in the sample. Is that true? Right? This is by definition. Remember, you never answer a probability question without the definition. It just won't happen. So you now need to read off 2 numbers here. Okay? You say, well, what are the numbers? You need to know how many men were on the Titanic, and you need to know how many passengers were on the Titanic. Is that right? So in this table, how many men? You told me 1,600 and what? 92. Okay, how many passengers? 2,223. So this is the fraction you're going to have to enter into your TI. Now, you probably have a question here. The question is, Mr. Judge, what do I approximate this to? I'm going to say we're going to approximate these to the nearest thousands, okay? Typically, hopefully, I know on a test, I always indicate. So that's not going to be an issue. Okay, let me get this out of the way. So on a test, I always indicate. I say like thousands here. Okay? And so how many decimal places is thousands? Is that 3? Okay, so let's go to the TI now. Let's find that there. And I'll scroll out a little bit, you know. So 1,692 divided by 2,223, okay? So what do you guys get here? 0.761 to the thousands position? Okay? So 0.761 to the thousands position, do you guys know what that means? That means this is a decimal. Every decimal can be written as a fraction. So this represents 76.1%. Just move that decimal 2 spaces to the right. So what I want to remark to you guys is this. This is what? This is 76.1% of the passengers were who? They were men. You say, well, how do we know? Because that was the question. This is what M stands for. So the probability of selecting a man numerically is 0.761, but that corresponds to a percent of 76.1%. Okay, so, you know, we know what percent of the passengers were men on the Titanic. All right, you guys okay with question number 1? Now, question number 2 here is the complement of being a man. This is non-men, okay? So I always put that, I highlight the non, the event is a man. Yesterday, you learned about the complement. So this is the number of non-men out of the total in the sample space, okay? So how do I determine what a non-man is? What do you mean if you're not a man? Does that mean you're a woman because you're not a man? No, it doesn't. Is that right? It means you're everything else but a what? A man. So what could you be if you're everything else but a man? You could be a woman or a who? Boy. Or a what? Girl. So how do we find that out, ladies and gentlemen? Yeah, so what you'll have to do now is this. You're going to say, and I'm writing it down. We're going to say, okay, how many women are on the Titanic? 422. Okay, how many boys? 64. Okay, how many girls? 45. Okay, you guys okay with that? So I'm writing it down. How many passengers? 2,223 passengers. Okay. So remember that discussion yesterday. If you're not a Republican, that does not mean you're a what? Democrat. You could be, or you could be peace and freedom. You could be libertarian. You could be independent, all those other parties. Well, if you're not a man, which you know is you're not a man, you could be a boy or a girl or a woman. So we'll go to the TI, and in the TI, we say, okay, TI, what do you do? Well, we do what? We take what? 422 plus 64 plus what? 45. You close that. What do you divide by? 2,200 and what? 23. And what do you get to the nearest thousandths now, ladies and gentlemen? This is approximately what? Yeah. It's going to go to the thousands. 0.238 or 9? 238 or 239? What do you guys think? 23 what? 9. Okay, this is a probability value. But when you talk to people at home, you can say, you know what? As a percentage, 23.9% of the passengers were not men. That's the complement of being a what? Man. Okay, you guys okay with that one? Now, I got something interesting here for you guys. Remember I titled this probability formulas? We have something called the complement rule for probability. We're going to use this a lot in this course. And it's called the complement rule. Now, here's what it is. The probability of an event plus the probability of the complement equals what? 1. Now, you might say to me, oh, how do we know that rule, right? Now, let me share with you guys where it comes from. Okay, this is total in the sample. every one of these dots is an outcome. This is a Venn diagram. So I got all these dots, ladies and gentlemen, here. And then I'm going to say this. This is everything that's inside E. Okay. So I put the boundary, and this is everything that's inside E. Well, there's some dots like this, this, and this. In fact, there's a lot that are simply not in what? E. Would you guys agree with me? Okay. But the total is in S. So what I'm going to say to you guys is this. If I count all the dots that are in E, all of these dots, if I count them, and then I add the number of dots that are not in E, you say, well, what are those? Well, these are all of these here. In purple. These are not in E. This is what I'm talking about. What should that equal? Do you guys know? That should equal the total in the sample. That's N of S, number of N of S. That's the total. So the logic is very simple. If I count everything in E, plus everything that's not there, that should be the total in the sample. Is that right? You guys okay with that? I'm going to use a little bit of algebra. I know from algebra, I can divide both sides by any non-zero number. So in this case, I divide both sides by N of S. Okay? On the left side here, I can distribute, I can distribute my division by N of S. And that will equal 1. Okay, you guys okay with that? Because anything divided by itself on the right side, N of S over N of S is 1. Now you may notice, hey, isn't this right in here the definition of the probability of an event? It is. Isn't this over here the definition of the probability of the complement of the event? It is. And then that equals 1. So, ladies and gentlemen, you're looking at a proof of what I just gave you. The complement rule for probability. Okay? This here is the proof of what I just said. This is why you care about events and their complements. Now, I want you to know you have equivalent versions. In other words, if I take this rule and I subtract P of V from both sides, this gives me an equivalent form, meaning the probability of the complement of E is 1 minus the probability of E. This is actually going to be what you use. Okay, we're going to use that version. And that's an important version to use. Okay? So, what is this called here that's equivalent? This is also known as the what? Complement rule. For what? Probability. Probability of a non-event is 1 minus the probability of the event. Okay, so in other words, you might even say to me, now, how do I use that? Let's take a look at how we use that. Remember this example we just did? Probability of selecting a non-man? You already know what the answer is. It's right in here. What's the answer? 0.239, is that right? Well, I'm not going to use the definition. I'm going to share with you how easy this complement rule is. This equals 1 minus the probability of selecting a man. So all I do is focus on the right-hand side now. What's the probability of selecting a man? You guys know this already. What is it? It's 1 minus 0.761. You found that in question number what? 1 here. That's the probability of selecting a man. This is gold, ladies and gentlemen. This is just pure gold. So now in the TI, I go to the TI now. And I say, okay, 1 minus 0.761 by the complement rule, and I hit enter. What do I get here? 0. What? 239. So this equals 0.239. And just like before, 23.9% as a percent. The blue is the answer because they asked a probability question. But, you know, we don't say there's a 0.5 chance of rain today. What kind of language do we use? 50% chance of rain. You guys see what I'm saying? So every decimal can be written as a percentage. So, but you want to be able to go back and forth. Understand what that means. Okay, so what do you guys think? Believe it or not, today I'm going to give you guys a couple of probability formulas, and that's what you guys want to use. So if you ever see the word non, okay, what do you think you want to use? What's the tip off if you see the word non? You want to use the what? Complement rule. Yes, outstanding. So number 2 is a complement rule question. Is number 3 a complement rule question? No, but number 4 is. Okay, you guys see what I'm saying? Number 3 is not a complement rule question. Number 4 is. So let's look at number 3 now. Let's go here. Okay. Here we go. Number 3. Probability of selecting a boy. What's that going to be? By definition, number of boys out of the total. Is that right? How many boys are in this table? We're using the definition. How many boys? That's my numerator. 64 boys. Good. How many people are there? 2,223. Okay, N of S. Easy breezy, lemon squeezy. We're going to approximate this to the nearest what again? Thousandths in the TI. 64 divided by 2,223. And what do you get? 0. What? 0. 2. Is that 8 or a 9? 9. Good. This is the probability. 0.029. It's the probability of selecting a what? A boy. What does that mean as a percentage, by the way? Yeah, 2.9% of the passengers were who? Were boys. So this is the event of selecting a boy. Now, you know what I want to say about this particular event? Is there anything we can say about this? What does that mean? Any probability that's smaller than 5%, what do we say? What was that definition I gave you guys yesterday? No, I gave you guys an important definition yesterday at the end. It's in your notes. It's not what? It's not likely you'll select a boy. Why do we know that's not likely? Under 5%, yes. Outstanding. This is less than 5%. So if that probability is less than 5%, we can say, I'll put that phrase over here. If it's less than 5%, it's not what? It's not likely you'll select a boy at random. It's under 5%. I bought lottery tickets today. I hope I win, but because I said it, I probably won't. You had a dream that you won? You had a dream you bought them? Yeah. Oh, really? I wish I had vivid dreams. I don't. Good for you. I wish I had them. Anyway. Let's look at number 4. Probability you select a non-what? Boy, what's the complement rule say? 1 minus the probability of selecting a boy. How do you know it's a complement situation? Non, that's the tip-off, okay? So, do I know the probability of selecting a boy? I sure do. It's 0.029. We figured that out in the last question. Is that right? So what is this approximately now, right? Go to the TI. Okay, TI. 1 minus 0.02 what? 9. What do you get? 0.97 what? 1. This is point what? 971. What does that mean? There's a what? 97.1% chance of selecting a who? A non-boy. Yes. Question. How did I get the what? How did I get the... Oh, that's a B. That's P of B. Right here. Probability of a boy. Now, this also means something here. Whenever you have a probability that's what? Bigger than 95%. Okay? Because you just computed this, it's 97.1. What do we say about the event? It's in our notes. What do we say? Nope, there's a phrase. What's that phrase? It's in our notes. Anything bigger than 95%, less than 100%, what does that mean? The event is, this event, almost certain, outstanding. It is almost certain. Almost. Okay? So if it's close to 1, you say, well, how close? Bigger than 95%, but less than 100%. We can say the event is almost certain to happen. So if you select a passenger at random, it's almost certain it's not going to be a boy. Non-boy. Good, ladies and gentlemen. Good. What do you guys think? Isn't that kind of interesting? Number 5. What was number 5? What'd you guys get earlier today? Oh, one of my favorite questions. A man and a boy. Now, let's go back and let's talk about this. Do you guys know you are selecting what? A passenger. What does that reference of A mean? 1. Good. If someone offers you a drink, it's only 1. If someone offers you a banana, it's only what? 1. If they offer you a birria taco, only what? 1. So we're talking about 1 passenger, okay? There's a passenger. They want to know what's the chance that passenger is what? A man and a what? Boy. So number 5. Okay. So the probability you select a passenger, it's a man and a boy. Okay. then that's the number of who? Men and what? Boys. Out of total number of passengers. So this is my definition. Okay? So I want to know. You say, okay, we already know there's 2,223 passengers. They're down here. But the real question is going to be the numerator. That one passenger has to be both a what? Man and a what? Boy. Okay? The key word here is what? And. So you're really going to have to think about this, ladies and gentlemen. Well, go to the list. How many passengers are both men and what? And boys. You might say, well, go to Excel. Let's see. Excel, where are you at? I went to Excel, and we're not even in Excel. There we are. There's what? 1,692 men, and there's what? 64 boys. How many are both men and boys? You have to be both, a man and a what? Boy. Are there any man boys in the room? Be careful, ladies and gentlemen. We can't ask the ladies that question. Are there any man boys here present? You're called a man boy. Say what? Say no. Why do you say no? You can't be both a man and a boy at the same time. Right? You guys understand what I'm saying? Can you be both a man and a boy at the same time? The answer is what? No. So this number here is 0. In your table, there are no man boys. It's philosophical. Okay. You guys okay with that? You got to be both. There's none. So what does that mean? What's 0 divided by any number? Now, in your notes, I left you guys with something. Anytime the probability equals, it must equal 0. What do we say about the event? The event is impossible. In other words, it's impossible for you to select a passenger on the Titanic and it be a man boy. That means you're both a man and a boy. Because a man is somebody who's at least 18. A boy is somebody who's what? Under 18. Okay? You guys see the language, how that's important? So you can't be both. Your age cannot be under 18 and at least 18. Okay, so I'm going to make a few observations here, by the way. I'm going to say, by the way. The list of men, intersection with the list of boys, is empty. You go, what in the world are you talking about? Yeah, the Venn diagram picture of this situation. If I put the name of all the men and I put the names of all the boys, I put them on a list, that intersection in orange, we say is empty. In other words, this is a picture of what's known as mutually exclusive sets. In other words, for short, there's simply no what? There's no overlap. Can't be both. And that's another important idea. Being mutually exclusive, no overlap, cannot be both at the same time, okay? So you can't be both a man and a boy, like you can't be both a what? Woman and a girl. Are there any woman girls? No such thing as a woman girl. Being a woman, you're at least 18, right? Being a woman, a girl, you're under 18 in terms of your age. So that's one observation I'd like to make. Another observation I'd like to make. Yeah, that's one observation. Sorry, it's the only observation. So you got to be aware. Sometimes mutual exclusiveness happens. You can't be both. Can you be both on time and late? No. Notice what I'm really saying here, okay? You might be confusing the word and with the word what? Or. You could be on time or late, but you can't be on time and late. And in fact, you guys know there's really two types of ors in the English language. There's two ors. One is called an inclusive or. The other is an exclusive or. Yeah, it's pretty fascinating, the word ors. The word or, you might say, wow, I didn't realize there's such a big deal about and or. There is. Let me express this to you guys here. Number, what I want to give you guys is number actually 8. I should have titled that number 6, but this is number 8. See that word or for number 8? Let's talk about the difference. Let's compare and contrast. Number 8, the probability of selecting a man or a boy. That can happen. This word or. Or. Let's think about this. What if I told my daughter, anybody, do I have any Disney freaks in the room? Like a Disney freak? My daughter's a Disney freak. She likes going to Disneyland. I don't know why. It's not necessarily the happiest place on earth, in my opinion. You guys know what I mean? It's miserable. Food's bad, too many people. They get in front of you and they don't care. You guys know what I'm talking about? You're tripping all over each other all the time. Anyway. So growing up, my daughter would want to go to Disneyland, and I would say, Ashley, you can go to Disneyland if you cleaned your room and you eat all your vegetables. What does she have to do to go to Disneyland? She got to do both things. Is that right? Okay, pretty simple. However, what tends to happen with people, right? She says, Dad, I cleaned my room. Can we go to Disneyland? And I have to say what? No, why not? She didn't do both. It's that simple. What if she came to me and said, Dad, I ate all my vegetables. Can I go to Disneyland? I'll say no. Why? She has to do both. She's thinking of the word or. And it's an inclusive or. You see, I never said we'll go to Disneyland if you clean your room or eat your vegetables. Because in that statement, you could do either the first thing or the second thing or even both. That's an inclusive or. Inclusive or means you can include the possibility of both things happening. So there's really two types of or. You say, what's an exclusive or? Where both can't happen, right? Like you're either on time or you are late. You can't be both. So that word or has flexibility. Is that right? You guys see what I'm saying? The word and does not have any flexibility. So what I want to share with you guys here is this. If you see the word or, that's really code for another formula. Okay? You guys ready? Yes. It's one formula. I'm going to share with you guys the formula. One formula. When you have the word what? Or, we use what's called the addition rule for probability. And I'm going to prove that one to you guys as well. So typically when I ask these kind of questions, this is the trap people fall into. Not knowing the difference between the word and the word or. So here's the addition rule. Okay, here we go. The probability of A or B, that's on the left side. In other words, you have the word what? This is or, two things, A or B. It's really simple. You compute the probability of A, you add it with the probability of B. I guess that's why they call it addition. And then you subtract it with the probability of A and B. So I'm going to get out a couple of colors. Here's purple, okay? You see that A? Here's brown. You see that B? Now you have the word what? And. This is the addition rule for what? Probability. You guys want me to prove it to you guys? Okay. The proof involves, again, yet a Venn diagram. We got 11 people at home today. This is everything that's in A, okay? All these dots, we're going to count them. And then this is everything that's in B. Notice some things are in both, okay? So I'm going to count the number of things that are both in A or B now. Here's how we count. It's based on the addition rule for counting. Okay, here we go. We count everything in A. You go, okay, here you go, A. Everything's in A. So I'm going to take that N of A. I'm going to count everything in B now. Okay? So we count everything in B now. Anybody notice a problem? Yeah, the overlap is an issue. You say, what do you mean? This overlap was counted what? Twice. So how do we fix this? We subtract it once. Okay, so the overlap was counted twice. We fix it by subtracting it once. What's the overlap, though? That's the intersection with A and B right in here. So we subtract that. Easy breezy lemon squeezy. You guys okay with that? We subtract it now. Now you divide both sides by what? N of S, because you can do that with equations. And then on the left side, you'll get N of A or B over N of S, and that equals N of A divided by N of S. That's N of B divided by N of S. That's minus N of what? A and B divided by N of S. What do you guys see as the definition on the left? That's the probability of A or B. This here is the probability of A. And then the probability of B minus the probability of A and B. Now, this concludes the proof for the addition rule for probability, and you apply it whenever you see the word what? Or. So this is why I put it right here, your addition rule for what? Probability. So let me remind you what we're trying to answer here. Man or a boy? So how do I use this? Do you guys know? What do I need to compute? I'll put it right here. Probability of selecting a man plus the probability of selecting a boy. Is that right? Minus the probability of selecting a man and a boy. Because here's the word or, and there you have and. You guys want to know something? You already found the probability of selecting a man. Let's see. What is it? It's over here. What is that number? Yeah, is it the first question? Look at that. 0.761. Okay, first question. Right in here. 0.761. This is what we just found. Do you know the probability of selecting a boy? We just found that one. Where is that? Probably a boy. There we go. It's what? 0.029. Is that right? So we take 0.029. Now, what's the probability of selecting a man, boy? Did you guys notice? We found what that is too. This one is what? 0. We subtract 0 there. You say, how do I know? We just did it right here. This is the man-boy question. 0. So in order to answer the or question, ladies and gentlemen, we just strictly have to do this what? Arithmetic right in here. Because if you subtract 0, that doesn't mean anything. Okay, it's strictly the addition rule in this case. So that's not the TI. Jeez. There's the TI. Here we go. 0.761 plus 0.02 what? 9. Ladies and gentlemen, what do you end up with as an answer? 0.79 as an answer. And you might even say, I thought you had to go out to 3 decimal places. Well, you can put the 0 there. And that means, by the way, what? 79%. So 79% of the passengers on the Titanic were either men or boys. Does anybody happen to know? I'm going to say this, by the way. This is an important detail. Remember, language and process, a big deal. What does it mean to be a man or a boy? You guys know? I'm not saying and, because there's no such thing as a man boy. It's not a philosophical question. Right? You can't say, all men are boys. Philosophical kind of question. Do you guys know what I mean? If this was like, where do you study those kind of things? No idea. Oprah. The Oprah class. All men are boys. Is that right? Well, what does this mean? Do you guys know if you're a man or a boy? This is not and, this is the word or. You know what this means? This means you're a what? A male. Do you know that's the definition of being a male, by the way? You're a man or a boy? What do you guys think? So they might even ask, you, hey, what's the probability of selecting, ladies and gentlemen, a male? So the probability of selecting a male, you already know the answer because that means you're a man or a boy. And that equals 0.790 to the nearest thousands. So I just want to kind of, just throw that out to you because sometimes you might even see that question. It's not just even here in this class. You don't know where you'll be when they start asking you math questions, ladies and gentlemen. You don't know. Believe me on that. They ask, what's the probability of being a male? And your first issue is you don't know what a male is. Oh, it's a boy or it's a who? Man. And then you go, it's an or question. Okay, good. Then that's how you start to, this is how you answer those or questions, okay? All right, you guys okay with that? You guys know what I'm saying? Easy breezy, lemon squeezy. Just like I said, I typically used to tell this story. It's kind of a sad story. It's the math story. I know people go, boy, Mr. Judge, I hate math, this world math, and oh my God, I've been hearing that my whole life. I used to even say it myself, and I was foolish for saying it. I learned that math wasn't really the problem. The problem was me. It's kind of a relationship. If you don't give it love, it ain't going to love you back. That's just how relationships work. Sometimes, I talk to some instructors at times. They go, nobody loves me, say those kind of things. Like, you know what? And I say to them, if you want love, you better give love. And that's a philosophical question. But it applies to a lot of different things, even mathematics. So in other words, what am I really saying? If you don't give it the time and energy, it ain't going to do anything for you. It's not. It's that kind of situation. You don't earn it just because you think you deserve it or want it. I mean, it doesn't come to you. You have to earn. I'm sorry, let me rephrase that. You don't get it just because you think you want it and need it. You got to earn it. Give it the time and energy. If you do that, then it'll respond to you in a positive way. Just like relationships. You go, my wife doesn't love me. And the first thing I'll say, do you love her? You guys know what I mean? My boyfriend doesn't love me. Do you love him? So in other words, do you give or do you just expect to take? That's how math is. If you just expect to take, it will never give to you. So in other words, you put the time and energy into a lot of these details. So the story I have, it's kind of a sad story, but it's a true story. I remember years ago, I was probably 17. It's another old man judge story. I was 17. My aunt was 18. Yeah, it was one of those things. My grandfather was having kids at an older age. So my aunt was just she was actually 11 months older. And we both found out about a local job here in LA, out there in Boyle Heights, B of A. The First in Chicago branch is not even there anymore. So we both went to apply, both my aunt and I. So we applied. And after we filled out an application, you know what they said to us? They said, okay, we're going to give you a math test. You just showed up to fill out an application. Who signed up for that, right? You go, math test? Oh, my God. So it's like, okay, we'll take the math test. My aunt, you know what she said? She said, can I have a calculator? You guys know what I mean? I never asked for the calculator. She asked for the calculator. So they gave us a test. It says, no. They told her, no, we're not going to give you a calculator. We want to see if you know some arithmetic. It was a bank job. You guys know what I mean? It's a bank job. Give me a calculator. So we both take the test. Without a calculator, I passed. She didn't. Who do you think they hired? They hired me. Then they didn't hire her. So I had the job, and it was a pretty good paying job for a kid who's 18, out of high school, working as a bank teller. You guys know what I mean? It was a pretty good job. She didn't get the job. So you might say, okay, what does it have to do with anything? I always think about that because later on, she just didn't work for a while. You know what I mean? She didn't, when she went to school, we went to ELAC together. She wouldn't go to her classes even. Her and her boyfriend at the time, Hector, they didn't go to classes together. And then they both never really done. Years later, she got married and moved out to, where did she move? Out to the desert somewhere. Victorville. How did you know that story? They go to Victorville? Sorry. My apologies to Victorville. Yeah, she moved to Victorville. There you go. Now you came back. She moved out to Victorville. Now, the reason it's kind of funny, because she's away from the family. She's out in Victorville, and she used to joke and say her best friends are tumbleweeds. Are there a lot of tumbleweeds out in Victorville? Yeah, that's her best friend, she said. My best friends are tumbleweeds. Okay. And I always go back and I think, you know why she's in Victorville with the tumbleweeds? Because she asked for a calculator to use that test. She didn't know arithmetic, ladies and gentlemen. I still think about those things. You guys know what I'm saying? What's the moral of the story? You never know where you'll be, and they ask you to do a test on something. Could be even, do you know the definition of a male? Do you know how to use the addition rule? Can you add? Can you convert a decimal to a percent? You never know when that's going to come. That's what I think at the end of the day. You're like, wow, never know. And I'm just so glad I knew. Yeah, apologies to all the people out in Victorville. Okay. It's kind of funny how you know the ending of the story. You're like, wait a minute. This is spooky. How'd you know the story? I don't know. I mean, I drive through it. It's pretty windy when I go through it. I don't want to know what the rain's like out there. Yeah. I drive through it on the way to Vegas. Huh? Oh, I have no idea. I just use the GPS. Is it? That long ride. That wrong, yeah. Victorville. Yeah, it's kind of funny. Huh? Never heard of that place. Is it really? Is the I have no idea. What'd you call? What's the name of it? Never heard of that one. All right. Believe it or not, there are people who survived the Titanic. What's the probability of surviving the Titanic? Do you guys know? This is going to be what? The number who survive out of the total. Let's see, how many people survived? All right. We know what do we know? We know the total, 2,223. That one's pretty good, right? So how many people survived? Can you read the table? 700 and what? 6. Good. 706 survivors. Let's see what this is. Okay, what'd you guys get here? Out to the nearest thousands. 0.31, not 7, but 8, because the digit to the right's a 5. Do you guys remember that? Okay, can you see that? You can sit in front. No. 0.318. What is this as a percent? 31.8%. So you know what that means? That means like 31.8% of the passengers what? Survived the Titanic. So there were some survivors. 31.8% survived. What's question number 7 now, ladies and gentlemen? Oops, sorry, I don't have 7. 7 is right here. What's the probability of non-surviving here, okay? I'm going to say use the what? Use the complement rule. The probability you don't survive. 1 minus the probability that you do what? Survive. Do you happen to know the chance of surviving? Say yes. Because we just figured it out. It's 0.318 over here. Is that right? Okay, see what I'm saying? 0.318. One minus 0.318. What does that give you guys? Point what? Isn't that 0.682? .682. And that's 68.2%. So 68.2% of the passengers, ladies and gentlemen, did not survive. Now, what is not surviving, AKA? Died. The complement of surviving is dying, though. There's only 2 options. You can survive or you can die, which is non-surviving. So this is the chance. This is why we call it a mortality table. It's like a mortality rate. Meaning the chance of you not surviving is 0.682. No, like similarly, kind of. That was in a different. Well, no. Yes and no. It was in the topic called conditional probability, which we're going to head to in that topic. But it's like I said, you know, when you look at this stuff, don't look at it what. I mean, don't take it personal. You go, you know, I was planning on going on the Titanic, Mr. Judge, and you just ruined it for me. You know what I mean? Nobody's trying to ruin your cruise, ladies and gentlemen. We're just giving you the what? The data, the information. Right? See what I mean? It's that kind of thing. 1682. What do you guys think? Is that pretty good? Now let's see if you're really awake. You got a milkshake? A Monster? Those are dangerous. Huh? Yeah. I'm going to ask you this question, even in relation to the yesterday. You guys are going to use the Titanic table. What is the odds for question number 1, surviving? Question number 2, odds for being a woman. Question number 3, odds for being a girl. Odds for dying. Okay, and you might say, what is this? These are odds questions. Didn't we work on that yesterday too? Right? Odds for, I gave you that definition. Okay, so let's give you guys some time. How long do you think that will take you guys to do this? Let's try that out. Let's see what you get. All right, everybody. Let's try to work with what we did yesterday, right? Remember, odds is another way of measuring chance. Is that true? Okay, so now remember, this is odds for, so you need the definition. So the definition of odds for surviving, number of survivors to what? Number of non-survivors. So I'm going to move these down. So look at the table here. Okay? How many people survived? 706. Good. How many people did not survive? So, ladies and gentlemen, you are looking at the answer 706 to 1,517, okay? So you guys are looking at the answer. However, I also want to say something about this. What else do we say? What's the best thing you guys can do for odds and ratios? Unitize them. Outstanding. Good job. So I want you guys, let's unitize the first number. So you might say, what do I do there? Divide both by 706. Now the second number, the first number is easy. You get 1, 2, but we're going to approximate to the hundredths. 1517 over 1706. So we go to the TI, and let's clear that out. 1517 divided by 706. And what do you guys get? 1 to 2 point what? Nearest hundredths. 1, not 4, but what? 5. Okay? Okay, so let's think about this here. And this is a very good way to think about these rates. What does that mean? That means there's one survivor to every 2 point what? 15 non what? Survivors. Did I make a mistake? 1517 divided by 706? No, I think we're fine. Yes, question. Did I make a... Oh, good question. Here's the question. Why don't we use the 2,223? Because in the definition of odds, there's two numbers. Number of survivors, that's right here, to the number of non-survivors. That's not N of S. The probability definition is N of X. So if they ask you a different question, it's a different definition. Well, what's the question? It's right in here. What's the question? The odds for what? For surviving. If they ask a probability question, what do you guys use? The probability definition. That's the difference. This is something, like I said, when people say to me, I don't know how to answer a question, the first thing I ask them is another question. What are they asking you? And you want to know what happens? People say, I don't know. And then I'll sit down and say, okay, let's read it. What does it say? And in one case, it'll say probability. That tells me they didn't know the probability definition. You want to know it. Just like this one, odds definition. Okay? And they're different. So you don't want to confuse them either. Yeah. No, you put it right here. This is it's the definition right in here. This is your definition. Oh, non-surviving for odds 4? It's the number of non-survivors to the number of non-survivors, which is survivors. But yeah, it's just knowing again your what? Your definitions. And everything that you do, believe it or not, in college, any subject that you take, it doesn't matter what it is, they all have their definitions, right? Like you guys were saying earlier, you like psychology, I guess, right? Because you find it interesting. Are they definitions there? What's the definition of, don't test you, borderline? Huh? I have no idea. What's the definition of, is there even a term called borderline, or am I leaving part of it out? Borderline schizophrenic, borderline, do you guys know what I'm saying? I have no idea. What's the definition of odds for selecting a woman? It's the number of women to number of what? Non-women. Every topic has its definitions. Okay? That's the key. So could you tell me, reading the table, how many women are in this table here? 422. Good job. Okay. Now, how many non-women are there? You know what I would do? I take 2,223 and I subtract the 422. Is that right? Do you guys see what I'm saying? I take the total and I subtract the number of women. That's the number of non-women. So there's a little bit of critical thinking there. So in the TI, 2223 minus 422, borderline. Okay. Is it 1,801? Okay. So the ratio will be 422 to 1,800 and what? 1. Now remember, this is your answer. But very often, it's not in the most useful format. Meaning, you can say 422 to 1,801. That's the odds for selecting a woman. What do you really want to do with that? You want to unitize. Yes. So divide both of those numbers by that first number to unitize it. So you're going to get 1 for the first one. But yeah, 1801 divided by 422, right? We're going to have to use a TI. So we say 1801 divided by that 422. Ladies and gentlemen, what do you guys get? At 4.2, let's go to the nearest hundredths. Is that 26 or 27? 27. So it's good that we know how to unitize. However, let's remember what the definition really tells us. Okay? There's one, what? Women to 4.27 what? Non-women. It gives you a better idea of the relationship when you unitize. So we unitize this here. One woman to 4.27 non-women. Like there's one survivor to 2.15 non-survivors. What about the next one? The number of what? Girls to the number of non-girls. Number of girls to number of non-girls. And here, the number of people who died to the number who did not die. Okay, so let's read the table. How many girls are in this table? Okay, and then how many non-girls are in the table? I can do the same thing. 2,223 minus that 45, right? And I'll get 45 2. Let's get out the TI. $2,100 and what? 78. This is the odds for selecting a girl. Okay. So remember again, it's like, well, that's great, but, you know, unitizing it is a lot more what? Interesting. It puts it into context. There's one girl to how many non-girls? Let's do some arithmetic with a calculator. Take the prior answer, 2,178. What do you divide by? Divide by 45. What do you end up with? That's exactly 48 point what? 4. Okay. So you say, what does this mean? Well, that means there's one what? One girl to every 48.4 non-what girls. Okay, it's a ratio. One girl to 48.4 non-girls. And what does it mean to be a non-girl? You're a woman, you're a man, you're a boy. There's 1 to 48.4 there. Yes. Oh, why 45? When you unitize, see that first number? I don't know. Did I make a mistake? Maybe I made a mistake. Oh, no. Because there's 45 girls. 45 girls there. Okay. Okay. Now, how many passengers died again? 1,517. Yeah. So if you're awake, you can understand that not dying means surviving. And yeah, there's 706 what? People that survived, or they did not die, right? So let's unitize, because like I said, it kind of, you want to really put it in a perspective. So we're going to divide by that first number again. So this will be, when we unitize, it becomes 1, 2. Now, 706 over 1517, that's going to be another decimal. It's not even a whole number, but that's fine. 706 divided by 1517. And to nearest hundredth, I guess we're doing that, 0.47. Okay, 0.47. The 6 is in the hundredths position. The digit to the right is a 5. So that means add 1 to the 6. And it's 0.47. So here's my unit ratio. And that's the what we say the death to non-death ratio, or the death to survive ratio. For every person that died, about 0.47 survived, did not die. Okay, and so I would say to you, in a lot of analysis purposes, to analyze data, it isn't just good enough to get the ratio for odds. You want to unitize it. It's kind of like if I said to you guys yesterday, there's one man for every 3 women, non-men, in a location, or, you know, maybe you like the other odds, whatever. It's good to look at it that way versus, oh, there's 48 to 96 type of thing, you know. Yes. Yeah, odds. Remember, we had 2 definitions. One's odds for, and the other one's odds what? Against. So, and they're ratios. You're right. It's a ratio. So like in Vegas, you might even say to me, well, why do you want to even bring up the word odds? And, you know, we talked about probability and we talked about odds. Well, because like I said, there's different environments that you'll be in. And they'll refer to things in terms of probability, or they refer to things in terms of odds. depending on the situation. Gambling likes to use odds. You might even care about, where are all the Dodger fans in the room? Any Dodger fans? There are none? Maybe only one? You know, so every year you guys might read, I know I do, and they'll give you the odds for the Dodgers winning the World Series. It might be 1 to 2.18. And then people go, what does that mean? Well, 1 chance of winning to every 2.18 chances of not winning. And then you compare that to like the New York Yankees or the Houston Astros or the Atlanta Braves, right? They'll give you those odds comparison, 1 to now 3.85, 1 to 5.63. And you go, oh, I can understand what they're trying to purvey. And that's what we're doing. We're trying to communicate and understand that meaning, but it's all done in a numerical way. And, you know, that's kind of how this goes. Anyway. Should we take a break? All right. Well, let me get out the language of break. Isn't it good to communicate? We'll put what? What do you guys do in your break? Take a nap? Are you playing that Xbox again? If you put the same time into doing homework as you put Xbox time, woo, you might be a what? Straight A student. Is that right? You guys know what I mean? All right. Okay, ladies and gentlemen. Okay. So, let's see what we get doing this together here. So, question number 1. Again, we know these are probability questions because why? They say probability. So, the first event here is what's the probability of selecting a what? Queen. So question number 1, we're going to use the definition of probability here. What's the definition? Number of queens divided by the total number in the sample. Is that right? And let's try to see if I can get that a little better. Okay. So look at yesterday you guys drew the picture. Hopefully that's in your notes. You guys want to memorize this. How many queens are in a standard deck? Good job. 4. How many cards? Now both of these numbers are divisible by 4. 4 divided by 4 is 1. Let's stick with blue. Not a big deal. And what's 52 divided by 4? 13. So this fraction is 1 over 13. Yes, you want to reduce your fractions. There's your first probability, ladies and gentlemen. This is how you answer the question. And you do want to have knowledge of the standard deck. Good. So that's the first question, okay? You guys okay with that one? Easy breezy? What's the second question? Chance you select a diamond. Okay. Probability to select a diamond. This is number of diamonds out of the total. So we're going to now look for diamonds. Which one are the diamonds? The second row, is that true? How many diamonds are there? 13 diamonds out of how many cards? 52. Now, it just turns out both of these numbers are also divisible by 13. So it'll be 1. 13 goes into 13 once. 13 goes into 52 4 times. So this would be 1/4, ladies and gentlemen. And that should make sense because 1/4 of the deck is actually diamonds. Okay, you guys okay with that? Easy breezy lemon squeezy? Right. All right, good. Now, what about number 3? What do I use for number 3? Yeah, but what was the formula? Remember, today we got got a couple of formulas today. The complement rule for number 3. So you might say, how do I know I use the complement rule? If you ever see the word non in front, like we do, we'll write it down. The probability of selecting a non-queen will be, by the complement rule, 1 minus the probability of selecting a queen. See that non? The event is a queen. We're using the complement rule. Now, here's what's going to happen here. Okay, this is a little bit of some arithmetic with fractions here. What's the probability now of selecting a queen? See, I have to know this chance right here. Is that right? And what do you guys notice? You might say, Mr. Judge, I see 2 answers. I see 4 out of 52, which is equal to 1 out of 13. So which one do I use? Use the reduced fraction, 1 out of 13. Okay, yes, that's the same as 4 out of 52. Now, what you're really looking at here, this arithmetic, you're looking at arithmetic with fractions. A whole number minus the fraction 1 over 13. Now, do you guys remember, how do you actually subtract fractions? Do you guys know? As I get my water. Yeah, you got to have the same denominator, but you say to me, I only see one denominator. I see the fraction 1 out of 13. I'll say, okay. This is over 1. Now there's 2 denominators. Is that right? And you can only subtract fractions that have the same denominator. So I'm going to share with you guys a little trick. See that 13? I'm going to multiply this fraction here, the bottom by 13, and the bottom by 13. Top and bottom by 13 for that first fraction. So you get 13 over 13 minus 1 over 13. Do you guys know that trick here? You got to use that same number. Right? You guys okay with that one? You guys see what I'm saying? That's something that you'll see. Now you can actually do what? Now you can subtract fractions. Why do I know that? Do you guys remember? I'm going to put A over B minus C over B. These are now like fractions. They have the same denominator. You keep the denominator and you subtract the numerators here, okay? This is the arithmetic you use. So what is 13, right? You say this is 13 minus 1 over 13. What is that going to be? You get 12 over 13, ladies and gentlemen, and that fraction's reduced. Guess what? You're done. That is what? That's what you get by using the complement rule. This is why I wanted to go over this here with you guys. Okay, I'll put the answer right here. But this is why I wanted to go over it with you. What do you think? Is that pretty good? Yay, nay? Is that all right? You guys okay with that one? All right. Wrong button. Okay. What about number 4? Is number 4 a complement question? How do you know? It says non-diamond. Okay. So we're going to try this process again. Number 4. Chance you select a non-what? Diamond. What's this? 1 minus the probability of selecting a what? A diamond. Okay? Do you guys happen to know what that probability is? We already did it. What's the chance of selecting a diamond? What's the fraction, the reduced fraction? 1/4 right here. We already did it. Is that true? So use that reduced fraction version. Otherwise, you're going to reduce anyway. So this is 1/4. We already answered. That's a chance of selecting a diamond. This is the complement rule. Okay? You guys want to get used to that rule. Now, this denominator is 4, okay? How do I subtract a whole number, or I should say a fraction, from a whole number? This is over 1. What do you guys use? 4 times 1. 4 times 1. That's a nice, neat trick for subtracting a fraction from a whole number. Do you guys know that trick? Right? You guys remember that? No? Oh, this is new for you then. Oh, this is new. Too bad they took those courses away where you did arithmetic with fractions. Because I have found really, like I said, you know, what's the key really being able to do math? It's arithmetic, ladies and gentlemen. Even arithmetic with fractions. If you're like good with arithmetic, you can do anything. Anything. Arithmetic with fractions, arithmetic with decimals, you know. Just arithmetic. In my ideal world, everybody would focus on learning what? Arithmetic. You would read, you would write, you would do arithmetic. You know what else you would do? Maybe you'd go run too. You guys know what I mean? Get some exercise. And then maybe you do some art, whatever that art is. Whatever it is. Maybe you like to draw. Maybe you like to paint. Maybe you like to write music. If we just did that every day, that's a good deal. What do you guys think? Should we change high school and middle school? Make sure everybody just reads, writes, go to PE and run. Okay, play basketball, whatever. And then do some art. What do you guys think? That's how you do it. How do they do it now? I don't know. Who just came from high school? Anybody know? How do they do high school now? Do they do any of that stuff? Join the club. Neither did I. Mm-hmm. I didn't do any of that. Yeah. What kind of classes you guys take in high school? Do you guys know? Huh? I don't know. I know. I'm sorry I even asked. All right, let's finish this off since you guys took all those courses. What's 4 times 1? What's 4 times 1? Do you guys know the number 1 is really like 4 over 4? Isn't that interesting? And then you subtract what? Uh-oh, we got a comment? Uh-oh, Jason. Uh-oh, we got to be careful. Uh-oh, I don't know. Does it do that? I don't know. I just use my head. I just do it this way. I have no idea. What's 4 minus 1? What does that give you? 3/4, ladies and gentlemen. What do you guys get? 3/4. Just to let you guys know, that's the deal. That's pretty nice. Doing some little bit of arithmetic, not even much. So this again is the complement using, this is the probability of a non-diamond, the chance you select a non-diamond there, okay? So I just wanted to go through it again to see if you guys can do it. And 5 and 6 is interesting. What do you guys... Diamond, there was the D. What do you guys know about 5 and 6? Because you see the word or, what do you guys use? The addition rule. Okay, so I'm going to move this out of the way for now. I don't know what happened. Did I move that or did I copy? Yeah, I copied it. Okay. So let's just get rid of it and we'll bring the other one down when we need it. How is this the addition rule? Because the word or. So you're going to ask me, Mr. Judge, anytime you see the word or, do you use the addition rule? What do you guys think? Yes. What is the addition rule? Let's write it down. Probability select a queen or a diamond. What does that equal? Probability selecting a queen plus probability selecting a diamond. Why is it probability selecting what? Both a queen and a diamond. So I write it down. Okay, I write all this stuff down because I want to remember it when the time comes. Okay, so notice this. This is the addition rule for probability. And if you need to, to see it, I'll even put the different colors. And I guess this was or. And this is the and. Remember that and? Okay. So you already know a few of these questions. A chance you select a queen, you knew is what? 4 out of 52. Is that right? What's the chance you select a diamond now? 13 out of 52. So we know those already. If you need to verify it, go ahead, take a look. Take a look at your standard deck. Okay, you guys okay with that? All right, now, what's the chance you select a queen and a diamond? Is there such a card? Let's think. The card has to be a queen, and then it has to be a what? A diamond. And, of course, the diamond is red, so let's color that red. Is there a card that's a queen and a diamond? What's it called? Queen of Diamonds. How many Queen of Diamonds are there? 1 out of 52, ladies and gentlemen. There you go. So, yeah, that fraction or that probability isn't always 0. In this case, the card Queen and Diamond is a Queen of Diamonds. Has anybody ever been the Queen of Diamonds for Halloween? You say there is no Queen of Diamonds. What is there? There's a Queen of Hearts. Anybody been the Queen of Hearts for Halloween? Anybody dressed up the last Halloween? What were you the last Halloween? You don't know? You were a witch? Teletubby? Witch? Anything else? You're a cat? You know what my wife said to me she wants me to be for Halloween? Frankenstein. She says, next Halloween, you know what you could be? What? Frankenstein. I said, why? Because I already look like him? You guys know what I mean? It's because I look like Frankenstein doesn't mean I should be Frankenstein. You guys ever seen a nice Frankenstein costume? I don't know. I haven't seen one. How do you be Frankenstein for Halloween? Have to be green, yeah. Maybe green, put some bolts in my neck. Weird. Frankenstein. Anyway. What's nice about this question? What do you guys notice about the denominator? 52, 52, 52. So I keep the denominator. The fractions are like. I just add and subtract the numerators here, right? So what's 14 plus 13 minus 1? 17 minus 1 is what? This is, the answer is 16 out of 52. However, ladies and gentlemen, isn't that what? Isn't 2 going to 16 8 times? I have to reduce the fraction. 2 goes into 52 26 times. 2 goes into 8 4 times. 2 goes into 26 13 times. And ladies and gentlemen, you're done. This is your answer. 4 over what? 4 over 13, ladies and gentlemen. Probability of selecting a queen or a diamond. Nice question. All right, what was number 6? If I'm awake, let's see. Yes, I do have number 6 here. Chance to select a queen or a king. What rule do I use again for this? The addition rule. Good. So I'm going to start to write it down here a little because I don't like running out of space. The probability of a queen plus the probability of a king minus the probability of a queen and a king here. Okay, so if you do like the colors, I'll keep that. Sometimes people prefer that because it allows them to see, right? Or, okay. So whenever you have the or question, you use what? Addition rule. Answer the individual probabilities here now. So you already know some of these probabilities by now, right? The chance of a queen, 4 out of 52. The chance of a king, what's the chance you select a king now? There's 4 kings out of what? 52 cards. Okay. So this is also 4 out of 52. Now, what do we know about the last probability? We have to have a card. And that card has to be both a what? A queen and a king. Okay? Are there any cards? This is the and question for the last probability out here. Right? That probability, which is right in here. How many cards are there in the deck of 52? You say, oh, is that 52? Well, yeah, there's 52 cards. But how many are both a queen and a king at the same time? Are there any, how do you say that? Queen kings? No. So that's 0. Is that true? So that probability equals 0. So what you're really doing is you're taking 4 over 52 plus 4 over 52. And what does that equal? It'll be 8 over 52. Is that right? Because you have the same denominator. Okay. There are no queen king cards. So what do you guys do? Divide the 8 by 2. You get what? 4. 52 divided by 2 is 6. Divide 4 by 2. You get what? 2. 26 divided by 2, 13. This is how we can reduce these fractions. And guess what, ladies and gentlemen? You answered another or question. Addition rule. Easy breezy lemon what? Squeezy here. So what do you guys think about those two formulas? What's the first one called? It's the first one that we did was called the complement rule, okay? When do you use it? Probabilities with the word non and non-events. That's the complement. The other one's the addition rule. When do you use that? Or. Okay, what's a good way to memorize those formulas? Every time you use it, you write it what? Down. Just like me. And maybe you said, I'm going to get some markers, some highlighters, and you use colors. That's fine. That's what I used to do back in the day. Colored pens even. So things can stand out, right? So you might say, well, how do you study? I'll share with you guys how you study. You guys really know how you study? When you do your, well, first of all, I'll tell you what I did. I used to take notes in class, and the first thing I did when I got home is I rewrote my notes in nice colors, right? Like black for facts and questions, like you see here. Blue for all my work, like you see here. Red for the important details, like you see here. Then I'd highlight my answers and put some of these quirky symbols like you see here. So I'm actually sharing with you how I rewrote my notes in my lectures. And then, I did all the examples. And then when I went to the homework, I did it with the same system. Wrote down everything that you guys see here in the same way on my own sheet of paper. Then, what did I do? If I didn't feel like I learned enough, I'd do my homework again. Sometimes I went to another book to see other questions. Because there's no rule that says just because they gave you 5 or 10 or 20 questions for homework, for you, that was enough. For me, I had to do like 30 or 40 because I was hard-headed. So I would do that too. And you want to know what I did the night before a test, though, by the way? You know what the best thing to do the night before a test is? You sleep. What? Yeah, you know what I would do the night before a test? I'd go to sleep and get some rest. And you go, really? Why would you do that? Because you want to know what happens on a test? Your brain might be tired if you stood up all night. And the first time you ever studied was the night before, and then you're panicked, and you stay up, and you fall asleep, and you get up again. Your brain on that test is going to go to sleep on you. Because your brain is going to tell you, you know what? Last night, I was supposed to sleep, and what did you do? You kept me up all night. So on the test, you know what I'm going to do? I'm going to go to sleep. And that's when people blank out. Okay, that's how it works. You don't think about it, but that's how it works. What do you do for breakfast the morning of a test? Well, what do you eat? You want to go and you want to go to IHOP and get pancakes and some bacon and a side of 3 sides of hash browns and you guys know what I'm saying? What's going to happen on the test if you eat that? You might want to go to sleep. So you have some brain food. What is some brain food? Have something light, like some yogurt, banana, orange juice, coffee. You know what I mean? Avocado toast, good. Something light. Then come in, relax. But you don't know the thing about it. Before you go to sleep, though, what do you do before you go to sleep? You review everything you already did. And you look at the nice, beautiful colors, and you go, oh, yeah, you can't have a card that's both a queen and a king. You can't have a man boy. Those probabilities are 0. You can have a woman girl. Those probabilities are 0. Oh, yeah, I remember this. Okay. Oh, yeah, the addition rule. Oh, yeah, the complement rule. Oh, I remember how to subtract a whole number with a fraction. Yeah, same denominators. You review the night before you go to bed. But you might say, when do I do all the work? Well, when do you do the work? Yeah, during the week, hopefully. The best case, during the week. when homework is assigned, the best case. The problem for you guys is you're in a short-term class. So you say, what does that mean? Well, it means every lecture is like 3 lectures. It means every homework night's like 3 homework nights. It's the price you pay. Now, some people like this situation because that's the only thing they work on, so they're happy about that. But what if you're taking like 2 or 3 classes in a short-term setting? I'm going to tell you guys the truth here. I would never take more than 1 class in a short-term setting. I would never do that. Even then, in all honesty, I'll tell you guys the truth. Even if my daughter came to me, she says, Dad, what is it, Ashley? I'm going to take 2 classes during a 5-week session. I would say, no, you're not. No, you're not, Ashley. Well, one of them's PE. I'll say, If you want, just take your PE during that 5-week class. Why would I tell people that I love these things? I think your sanity has value. I think you run the danger of concluding that you can't do things when you really can. I would never put myself in that position personally, and I couldn't advocate somebody that I love be in that position as well. I mean, people do eventually. Eventually people understand, boy, Mr. Judge, you were right. I go, you don't have to tell me. I already know I'm right. It's not that I feel like I'm right. It's because it comes from what? Experience. What I went through, what I've seen. It's all experience, ladies and gentlemen. Now, you might say, when it comes to me, it's different. Well, okay, maybe. What's that chance? There's a small chance. Maybe you are different. Maybe you can handle. I run across students that take like 20 units. I would never do that. The most I took was 15, and I never did it again. I learned that lesson. So, people are different, but I would still give you that advice. Don't try that. That's all I could do at the end of the day, give people advice. People don't always take it, but eventually they understand my point. The only concern, like I said, would be you might just conclude you can't do things when you really can. That's the worst conclusion you can make because you just may not have put yourself in that best position to succeed. And that's just the way it is. Okay? So it can be done. People have done it. I've run across a lot of students who have done well. Like, for example, I was thinking of this morning. I remember this student. She sat right here. She wasn't afraid of sitting in front. She sat right here. She was right there. I can still see her. She failed her first test. And she's like, I don't really know what I'm doing wrong. I said, oh, okay. Well, let's see. What are you doing? I'm giving her the same advice I give you guys. Turned out she just wasn't studying consistently every day. She was waiting till the last minute, maybe the weekend, night before. She was going out the whole weekend, having a good time. And then she got to things and she couldn't believe, man, you even gave me a study guide and I failed? She couldn't believe it. Right? She's like, what? The math doesn't add up. So I told her, why don't you try everything I'm giving you this advice to do? Try it this way. Do it this way. Do this. She took my advice. You know what she got in all of her exams in the final? A's. Not just A's, 100%. She couldn't believe it. She just couldn't believe that was even possible. She got A's. She finished the course, and I remember she actually got a scholarship to go to like a Cal State out like up north somewhere like Humboldt. Is there a Cal State Humboldt or something? Something like that. Chico is, I don't know what it is. It might even be Chico. Might even be further north. I think it's Humboldt. And I remember that because she came to my office and she's like, gosh, Mr. Judge, I'm so afraid. I don't want to go there. I'm afraid. I got to take my kids. She was a single mom, had some kids. And take my kids out to Humboldt. And I'm just afraid. I feel more comfortable staying here in East LA. And you know what I told her? Tell her the truth. I said, you know what? You want to think of it this way, okay? Go out there, have some fun, take your kids with you. Think of it like a camping trip or something, you know? You're going to take your kids, you're going to try this out. I go, what's the worst thing that can happen? East LA is always going to be here. You can come back. It's not a big deal. Didn't come back then. But give it a try. Don't be afraid. And enjoy your time there with your kids. You're going to look back and go, man, that was a great time. We were out in Humboldt. We got to see some trees. We're finally not even in a neighborhood that's the same. You know what I mean? Sometimes you got to get out of East LA. So she got out. She went, had a great time, graduated. That was the advice she took, but she was afraid. So sometimes people are just afraid. They're afraid of something different. They're afraid of trying something different. They're afraid of putting themselves out there because we're all comfortable about who we get to blame for everything. We're too afraid. You know, and I know that because I was just like her. I'm the same kind of person. That's how I know it so well. You know, so it's not just, again, it's a lot of experience. It's what I've seen. It's what I've been through. And I get it and I understand. But ladies and gentlemen, you can do a lot more than you ever realized. You just want to give yourself that honest chance. And don't ever be ashamed of the things that you might have done in your past that you're not proud of. Don't never be ashamed. Don't be ashamed of the things that have happened to you that you're not happy about. You got to move past it. That's the only way you'll grow. That's the only way you'll take those steps. If you don't do that, you'll be shackled in those sort of chains of doubt and insecurity, and that's worse, in my opinion. That's a lot worse. So the same advice I'll give her, like I gave you guys, go out and try that out that way, study this way. It changed my life, and I am sure, and I'm not just sure, I know it's changed other people's lives. They've done it the same way. Okay, you guys okay with that? All right. I should have been a preacher. Should have been a preacher. I should do it on I am. This is my podcast. This is the podcast. Who knows? That was my intention. That's why you see this stuff. But I'm kind of busy with a lot of things. Like, you have no clue. You guys have no clue. No, well, Daniel Judge. Yeah, I'm a DJ. Daniel Judge. No. It's, yeah, I don't know. I might still, we'll see. Who knows? Yeah, if I retired, I would probably do that. But I think, pray I win the lottery. Pray I win that $1 billion. You know what I mean? Pray. Because I don't know. I have no idea. Pray I win the lottery, and then I'll do it. Because there's the colors. Queen, King. There are the colors. It was better to see that way. I made a mistake. What did I do? They're supposed to be green. Because I keep praying to win the lottery. God hasn't listened. So you guys can pray I win the lottery for me. That way I could do that podcast. You guys know what I'm saying? Yeah, I know. I wish I can win. I wish I can win. Well, pray I win the lottery and let God decide to say, okay, finally you've been praying. You've been praying to win, and I've ignored you. Have I bought? You kidding me? All I do is buy lottery tickets. I've invested a lot of money in the lottery. That's all I know. And I haven't won. Well, actually, I'll tell you another real quick story about lottery, just in case you guys didn't know. It's kind of a goofy story. See, I used to always not win. I used to always read about people who won the lottery, and it was always like, yeah, somebody was driving through town on a road trip. They stopped by a liquor store and buy some hot dog buns, and maybe they just bought like a lottery ticket, and that was the big winner. And I would get so mad. I'm like, oh my God, you just spent $1 and you won. You were gonna buy hot dog buns, really? So random, you guys know. So I started to think, and I said, you know what I'm gonna do? Next time I'm out of town, I'm gonna buy lottery tickets. Just as a kind of a goof, it's always those people who are going out of town. I'm gonna try it myself. So I was going to Vegas on the way to Vegas, and my daughter was with me. We're gonna have brunch with my aunt out there, and drive out to Vegas. And then we stopped at 7-Eleven to get like coffee and get her milk and donuts or something. Gonna go and have brunch later in Vegas. So it was really early. So I went to 7-Eleven, I was getting the coffee, and there was like this commotion in the line. And I'm like, oh man, really? Like, I can't wait on, I was impatient. So I just told my daughter, Ashley, you know what? We're gonna go on the road. We'll get our coffee and milk on the road, and I'll get some lottery tickets. I'm gonna probably win. She goes, okay. She's a little kid. So sure enough, we go on the road and driving through California on the way to Vegas. And I forget what town it is. It might have been Bishop. You guys know you drive through? No, I'm not Bishop, sorry. What are the towns you guys drive through? There's a couple of towns you drive through on the way. Barstow and something else. I might have stopped in Barstow. And in Barstow, got off, got my coffee, got her milk and cookies or whatever she wanted, bought my lottery tickets, I don't know, like $10, continued to Vegas, and had my brunch with my aunt. So, on the way back, and so a few days later, I go, yeah, I got these lottery tickets. Let me check if I won. You know how many numbers I got? 4 out of 6 numbers. What? How much did you get for 4 out of 6? How much do you think I got? Like $500. Like, wow. Then I started thinking, if I just got one more number, it was $1 million for one more number. And I was like, oh man. And for 2 more numbers, you know how much I would have gotten? $200 million. It's like, man, why didn't I just continue to drive? Why did I have to stop him where I was? I could have went further and bought my tickets. You guys know what I'm saying? No. No, I wouldn't. No, I wouldn't. That's the truth. I'm not going to lie to you guys. I'm telling you the truth. I would not be here. I do like to teach, but there's just a lot going on that people don't know. That's just crazy. It's never about the students. It's never about being here with you. It's never about that. I'd rather be here than anywhere else. It's always about other things. You guys just don't know. There's a lot of other things going on. It's not just that I teach. I have a lot of roles and different hats I wear through doing what I do here. Like I'm curriculum chair for the district. I work for a faculty association as a lobbyist in the state for faculty. I'm on the statewide academic senate data committee, blah, 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 blah. So you do work there, and you get to see the reality. And when you get to see the reality, that's heartbreaking. What's really going on. I might start crying. Let's see who's here. What does Devin say? Oh, yes. 2 billion? Oh, 2 billion. The recent 2 billion power ticket was sold at the same gas station I bought mine from. I would have had a heart attack. I would have had a heart attack, Devin. I would have been, wow, that was me. And you find out it's not you. You know what I mean? You're like, oh, why? That's horrible. I would rather just not even go through the experience. So I do know, I'm kind of a little superstitious. The fact that I'm even talking about it, you know what that means? Ain't going to win. Ain't going to win. But I think God doesn't want me to win anyway. You don't want me to win. I would have won already if you wanted me to win. So that's the long answer. Do I buy lottery tickets? I have. On the desk, I think I have a stack this thick. I got to go through and see if I want anything. You know, like, man. Yeah. I think they do. I think they do. And sometimes what happens, because I used to keep them on my wallet, you can't read them. You try to see if you won. It's like, can't read or whatever. You're like, darn it, what if that was the winning ticket? You know what I mean? Chances are it's not. It's not likely to win, but it is still what? Possible. Yes. No, not the scratch. It's just like Mega, Powerball, those things. Yeah, I'm doing quick picks. Quick picks. I think they do. Even if you win, yeah. I don't know how long it is, but I think there are some expiration dates. So it might be. I think I heard that. They claimed it? 90 million? Yeah, that makes me mad too. It's like some rich old guy won 90 million and you're like, oh, man. Really? Yeah. It's heartbreaking. Anyway. There's people who win like that. And that chance, it's not likely. Probably is less than 5%.